Today, we are going to resume our discussions on the behavior of N wells for a CMOS integrated circuit. And before we get into this specifically, I want to take a moment to look at the design rules for N wells because they bear mentioning. Let's see, they're rule 1 point something, but that doesn't tell me what page they're going to be on at all. Just random tables. $31. You know what? Let me get my keyboard. Left, come on. There's 91 instances of it, so that's not going to help anything. I believe this is rule 1.1. Yep. All right. So there are 4 rules that govern how wells can be laid out. And our Moses design rules actually show us little pictures and stuff that try to help us understand these as well. So the first rule, number 1.1, is that the minimum width for a well is either going to be 10 lambda, 12 lambda, or 12 lambda, depending on our process. So I guess one thing that might be pretty useful for you guys to know is what the hell lambda is, right? Or what lambda means. So lambda is the minimum feature size for a CMOS technology node, okay? It varies process by process. So for the on-semiconductor C5 process, which was later named to B5 for reasons I don't know, the minimum feature size lambda was 300 nanometers, which effectively means that the gate of your transistor would have a minimum length of 2 lambda or 600 nanometers. TSMC, the Taiwan Semiconductor Manufacturing Company, they have processes as low as 24 nanometers with lambda currently, which means we're talking a real minimum feature size of approximately 48 nanometers or 50 nanometers for the size of the gates and all that kind of good stuff. So what we are going to be designing to is a sub-micron design standard for that middle column. So not the regular scalable CMOS, but also not deep sub-micron. We're going to be going for kind of the middle ground there. So the minimum width of a section of N well will be 12 lambda. The minimum spacing. So actually, before we move on to that, one of the reasons why the minimum width is 12 lambda, which probably seems fairly large, is because process engineers have figured out that anything less than 12 lambda, effectively you can't reliably reproduce it, meaning that you wind up with a very low yield when you dice up your wafer and all that kind of good stuff. So 12 lambda works out to be the minimum acceptable standard to actually have a yield better than 50%. Okay. The next bit here, the minimum spacing between wells at a different potential, so that's 18 lambdas. That's significantly larger. Okay. So I want to talk about exactly why that is. Wells at different. Okay. So I'm going to try to draw a side view of a substrate with a couple of wells implanted into it. And I believe to this point I've been using purple for end wells. I'm going to try to stay consistent with my colors as best I can. So we have two end wells here. And the requirement is that they must be 18 lambda apart if they're at different potentials. So let's talk about that if they're at different potential things, because that's pretty important as well. If we were using an N well as the body of a PMOS transistor, we would set that N well to be at the highest potential in our circuit, typically speaking. So that body connection would, if we had a 5-volt process, it would be at 5 volts and our substrate would be at ground, right? So I am just going to put plus 5 volts here. Now, if we have an N well that is adjacent to, but we're using it as a resistor, we wouldn't just have that entire N well tied at 5 volts, because that wouldn't make any sense whatsoever, right? If the entire resistor has a potential of 5 volts, it's not acting like a resistor at all because there's no voltage drop over it or anything. So if this guy is the body of a PMOS, and this guy is some portion of an N well resistor, and ostensibly the resistor is going to have a lower electrical potential than VDD because it's somewhere kind of downstream in the circuit, so there'll be voltage drops in front of it and behind it so that the overall electrical potential across the resistor is less than 5 volts. What happens is we have parasitic BJT, right? So we have an N-type region at a very high potential, a P-type region at a very low potential, and then another N-type region that's at some intermediate potential, which could potentially cause this N-well BJT to turn on, which is going to mess everything up. And those effects are going to be more noticeable the closer those N-well regions are to each other. So 18 lambda away is far enough away to where those interactions are effectively 0. Okay. Does that make any sense to any of you guys? All right. So if we looked back at our design rules, the minimum spacing between wells at the same potential is 6 lambda. Why is that? Thoughts? So will the transistor ever turn on if both of those N-type regions are at the same potential? Never. No. So that's why we can move them so much closer to each other. Okay. Our fourth rule here, the minimum spacing between wells of different type, and it says here, if both are drawn, is 0. And so this may seem awkward, right? You can effectively abut an N-well region right next to a P-well region and have no problems whatsoever as long as they're not technically overlapped. Well, the reason for this is that our field or our substrate is actually considered to be P-well the entire time, okay? So it counts as a P-well region to all of our design tools and stuff like that. So if we couldn't have an N well region right next to that P well, we couldn't have an N well region, period, because the P well encompasses everything for a P-type resistor, or excuse me, a P-type wafer. Okay. All right, so now that I have introduced the concept of parasitic elements, right? Parasitic diode, or excuse me, parasitic transistor, pretty easy to avoid. In fact, you'll get errors telling you change the spacing if it thinks it's going to happen. Parasitic diodes are another potential issue. And these cannot be avoided per se by a simple change in the physical dimensions of the N well. Okay. So when an N well is fabricated inside a P-type substrate, a PN junction occurs at the interface. So graphically, here's our substrate. Here is our N well region. And the N well region effectively acts as the negative polarity terminal. I say that because I can't remember whether cathode or anode is the one with all the electrons. I always get it backwards. And our substrate acts as the positive polarity terminal of a potential parasitic. Oh, I wrote it down. I'll be damned. So N well is a cathode, and a P sub acts as the anode. In CMOS circuits, the substrate is usually tied to the lowest circuit voltage, which is ground, which is going to keep this diode in a reverse bias region. Right. So the anode will typically be at a lower potential, lower or equal potential than the cathode. Keeps this diode reverse biased. Right. So what do we know about reverse bias PN junctions? What do we know about PN junctions in general? Let's start there. Thoughts? Hopefully you guys know a lot. You've had a couple of classes on them.
They only allow current to flow from the anode to the cathode.
Right, so they're a one-way valve for current, okay? So that is their principal use, but what's an alternative use for a diode? Anybody remember that kind of stuff? Like what else could it be used for other than a one-way valve? A capacitor, absolutely right. So what we have is, going back to the simplified look from 335. Let's say we have 0 bias conditions for now, right? So if this is the P side of the junction, and this is the N side of the junction, then what we should have is a bunch of holes, which I'm going to denote by circles. And in a region close to the metallurgical junction, so where the P-type material meets the N-type material, and I'm fully aware that we don't actually create these by fusing two crystals together. It's just the easiest way to kind of think about these things. So at that metallurgical junction, we have a bunch of ions, negatively charged ions on the P side because all of their holes have gone away, or actually they've recombined. Would be a better way to put it. And on the right side of the junction, we have a bunch of positively charged ions. And then deep into the N-type region, we have an abundance of electrons, which are going to be these little black dots, right? So we have a layer of bound negative charge due to the acceptor atoms losing their holes. And we have a layer of bound positive charge due to the donor atoms losing their electrons, because all in that region, everything's going to recombine. And we're left with that space charge layer, right? Or the depletion region, or whatever textbook you happen to be looking about that deals with PN junction calls it. It's got like 5 different names. I like the space charge layer because there's a space with charge in it. So that's how I think of it. The depletion region also makes sense to me because it has been completely depleted of free charge carriers. All the other names I can't remember because they don't have something that physically makes sense to me. So when we reverse bias this guy, so I'll actually, before we even get into that, because there is bound charge here, there is a capacitance, right? So anytime we have the physical separation of electrical charge, we wind up with a capacitor. 100% of the time, that's kind of the fundamental definition of capacitance. Well, when we reverse bias this guy, what happens to the size of the depletion region? One of 3 things can happen. Nothing, it can get larger, or it can get smaller. So if I were to apply, if I reverse bias this guy, that means I'm putting a negative voltage on this side and a positive voltage, or the positive polarity terminal of the voltage on that side. So let's think about what's going to happen. So if I have a negative voltage applied on the end where there are a bunch of holes, what are the holes going to do? They're going to move towards that negative voltage, right? Because the positive charge of the holes will be attracted to the negative charge of the negative polarity terminal. So that means that those holes are going to move over, and that's going to make the bound negative charge get larger, right? As holes move away from this interface and start heading this way, more and more bound negative ions are going to get uncovered as that positive charge leaves that region. The exact same thing, but opposite, is going to occur on the right-hand side, right? That positive polarity terminal is going to attract electrons, which is going to move the boundary of that positive bound charge region to the right, overall causing the space charge layer to get wider, right? So there is more charge being uncovered, but the region of bound charge is now larger. What effect is that going to have on the capacitance? So this is a simple, or we can model it as a simple parallel plate capacitor, right? For a parallel plate capacitor, C is equal to Q epsilon over A, right? So actually, that's not right. That's not remotely right. Epsilon A over D. I'm getting my C is equal to QV relationship jumbled into my parallel plate capacitor relationship. So excuse me. So C is equal to epsilon A over D. So even though we're uncovering more and more charge, the cross-sectional area of the plate effectively doesn't change at all, right? Because it is just that surface that's moving back and forth along the X direction here. But the distance between the plates can get appreciably larger depending on how far we reverse bias this guy, right? So we should see that as the reverse bias voltage gets larger and larger and larger, our capacitor value changes as a function of time, and it's typically going to get smaller. So we can say that our N-well behaves like a capacitance where it's going to be a simple junction capacitance. Oh gosh, let's see. I think this is about to start giving me a bunch of errors, but we'll see in a second. Cj is equal to Cj naught divided by 1 minus Vd over Vbi to the mth power, where Cj naught is the unbiased junction capacitance. Vbi is the built-in voltage of the junction. So effectively, that's the built-in potential that causes diffusion and drift to cancel each other out, which establishes the width of this phase charge layer. And then M is our grating coefficient, which I don't know that we talked about in 335 and 336. So I'll take a moment to talk about it here in just a second. It would probably be helpful to understand what Cj naught is. So Cj naught is epsilon A times Q over 2 epsilon Vbi multiplied by Na Nd over Na plus Nd, all to the 1/2 power, where epsilon is the permittivity of the material. That looks like I'm spelling it poorly. Permittivity. For silicon, this is 11.8 times the permittivity of free space. Q is our elementary charge, 1.60218 times 10 to the negative 19 coulombs. Na and Nd are our acceptor and donor concentrations. So this is effectively Na is the substrate doping level. And Nd is the donor concentration. And in, oh goodness, let's see, in our case, this is the N-well doping level. And gosh, we also probably need to have a reasonable idea of what VBI is. So I'm going to give you guys a minute to finish writing this down because it's going to force me to go to the next page. All right. our built-in voltage, PBI, is KBT over Q, natural log NA ND over NI squared, where, I know this is equations inside of equations inside of equations with constants inside of constants inside of constants. I apologize. KB is a Boltzmann's constant. Having a value of 1.381 times 10 to the minus 23 electron volts per Kelvin. Let's see, I already gave you guys what Q is, and I is the intrinsic concentration of the semiconductor material. So let's call it 1.45 times 10 to the 10 per cubic centimeter for silicon. I know for a fact this is a slightly different number than we used in 335 and 336, and it's also a slightly different number than what was given to you guys in 334. Every textbook has it different. It's always going to be between 1 times 10 to the 10 and 2 times 10 to the 10. But where it falls in that range is how it was measured. So something in that range is good enough for me. All right, so we have all of this jibber jabber. Let's talk about those grading coefficient things again. So I mentioned a couple of minutes ago that PN junctions aren't actually formed how it kind of looks like they're formed from all the pictures that we wind up drawing to explain what's going on in classes, right? So it might seem like you take a raw piece of silicon and then you dope part of it p-type. And then you take another raw piece of silicon and you dope it n-type, and then you smash that p region and that n region together, and magic happens and your space charge layer is formed. Cannot work that way, right? Not on this small of a scale or anything like that. So that type of junction can be loosely approximated by what's called a step junction. Okay, so that's a specific doping specific way of doping the crystal to cause it to almost be a perfect transition between the n-type material and the p-type material, where the concentration throughout the n-type is one thing, the concentration throughout the p-type is another thing. So for a step junction, step junctions are formed by an abrupt change from acceptor ions at the p side to donor ions at the n side, and have a grading coefficient of m is equal to 1/2. Okay, so if you look at those equations I gave you for junction capacitance as a function of the unbiased junction capacitance, if you looked in your 335 or 336 notes, I don't remember which one, that equation probably looks super familiar, but all that stuff on the bottom was underneath the square root. And it's because the textbook that we used said all junctions were step junctions, which is not remotely true. Okay. A linear graded junction contains junctions where the change from acceptor to donor atoms varies, sorry, not occurs, varies linearly with the distance from the junction. And have a grading coefficient of m is equal to 1/3. Linear graded junctions are what happen much more in practice, right? Because you're going to start by to try to form a PN junction by creating an N well, right? So there's an established amount of P-type material inside the substrate, and you implant that N well, right? So you're replacing a bunch of atoms in a specific region, and then thermal diffusion occurs. And so the level of concentration tries to balance itself out in that region, because that's what happens in diffusion, right? So you're going to see that the concentration gradients, instead of falling off, are a linear change as we move across the junction. So this is much more often what you'll actually see. So really, it should have been under a cubic root sign the whole time. But anyway. So let's say we want to define, we want to determine the depletion capacitance of an N well slash P substrate diode with dimensions of 100 lambda by 100 lambda, where lambda is equal to 300 nanometers, or a simple C5 process. Given that the substrate is doped with 10 to the 16 per cubic centimeter concentration, and our N well is doped with 10 to the 17 per cubic centimeter concentration levels. The measured zero bias depletion capacitance of the junction is 100 attofarads, so 10 to the minus 18 per micron squared, and the grading coefficient is m is equal to 1/3. Assume depth of the well is 3 microns. So I want to ask you guys a question that may not be obvious, but why is that last sentence, assume the depth of the end well is 3 microns, critically important here? Any thoughts? So let's say I'm going to draw the same picture again, over and over and over again for a little bit here. Here's our substrate. Here's our end well, right? It's very easy to see how the bottom of that end well region forms a capacitor with a substrate, right? Because it's all a PN junction. But we can't forget about the sidewall capacitance as well, right? Because our end well structure is a 3-dimensional junction now, right? So it's not simply, it's abutted against something, and then we have free space surrounding on all sides. So we have some sidewall capacitance as well that we need to take care of, all right? So let me write that in here. Sidewall capacitance and bottom capacitance. We'll have to figure out what both of those are. Now, luckily for us, how are the bottom capacitance and the sidewall capacitance electrically connected together? And I mean this from like a circuits 1 standpoint. They're in parallel, right? Because their top electrode, or whatever you want to call it, is that space charge layer bound inside the end well. And the bottom electrode is the space charge layer's contribution from the substrate, right? So even though it's a 3-dimensional capacitor, it's still those two things just simply connected in parallel, which means we don't have to do anything fancy. We can just find what each of them are and then add them together, because that's how capacitors behave, right? So how would we go about finding the bottom? I'm going to call it CJ0 B. This is the unbiased bottom substrate capacitance. How do we figure out what that value is going to be?
You multiply the area times 100 out of the.
Yeah, so we know what the capacitance is per micron squared. So we really just need to know what area to get the capacitance by itself, right? Seems fairly reasonable, okay? So that would be CJ0 times our bottom area, where our bottom area is the dimensions that we are given, right? 100 by 100. And then we're going to have to scale that by a factor of lambda squared, because we weren't given the actual physical dimensions of the capacitor itself, right? So that's going to look like 100 times 10 to the minus 18 farads per micron squared times 100 squared times 300 nanometers squared. And I get this to be 90 femtofarads. Okay. So that's what our overall unbiased bottom capacitance is. For our sidewall capacitance, CJ naught S, somebody besides Pierce, tell me how we might figure that out. So what does the 3 microns represent?
So the sidewall.
Right. So what else do we need in addition to the depth of the sidewall to figure things out? So if we just had the length, so let me be clear here. Let's call this unit the length. Is that what you were talking about when you were referring to the length?
Well, I mean, going into the finger, but yeah, I guess I could work.
So there's 2 things here that we have to take into account, right? So that length is a critically important dimension that we know is exactly 100 lambda, right? What I think you're trying to get at, but maybe you forgot the word for it, is we're going to need the perimeter of the well, right? That perimeter multiplied by the well depth is going to give us the total surface area that isn't the bottom capacitance. Does that make sense to everybody? Okay. So we're going to have CJ naught times the well perimeter times lambda times the well depth, which is going to be 100 times 10 to the minus 18 farads per micron squared. So what's our perimeter? 400 lambda, right? Nanometer times 3 micron. And for this, I get 36 femtofarad. So if we had neglected our sidewall capacitance, we'd be off by 40%. So it makes a significant contribution to an N well that's this small, really, right? Although 100 lambda by 100 lambda probably doesn't seem particularly small, but in the grand scheme of things, when our die size is 1.5 millimeters by 1.5 millimeters, this particular well would be what? So 100 lambda, so 100 times 300 nanometers. So that would be 100 times 0.3 microns. So 30 micron by 30 micron on the scale of something that's 0.5 millimeter by 0.5 millimeter. It's actually pretty tiny. So anyway. All right, so we know what our unbiased capacitance is, right? CJ is going to be CJ naught B plus CJ naught S. And then each of these are going to be divided by the cubed root of 1 minus VD over VBI where we have enough information to figure out what VBI is, right? So let me add these guys together first. That's going to look like 126 femtofarads divided by the cubed root of 1 minus VD VBI. Where our built-in voltage, I'm going to sneak that in up here. Is KBT over Q. natural log NA ND over NI squared. Let's say it wasn't mentioned that we're at 300 degrees Kelvin standard temperature. What's KBT over Q? Yeah, 26 millivolts. That's our thermal voltage. And so plugging in our numbers here, we would wind up with 0.759 volts as our built-in voltage, which we could then substitute in to this relationship and understand how our capacitance changes as a function of our applied reverse bias voltage. I think we're going to wrap up here for today because the next topic that I want to talk about, we probably could have done in a half an hour or so, but because we got started a little bit late, we couldn't get to it. So as a kind of spoiler here, we have observed that an N-well can be used as a resistor, right? Because it's a medium that resists current flow and all that kind of good stuff. However, when we use an N-well as a resistor, we're still forming a PN junction around the entire perimeter or around the entire surface except for the top surface, which is ostensibly exposed to. We're looking at it like it's air right now, but it's going to wind up being silicon dioxide, forming a reversed biased PN junction, which looks like a capacitor. So we have in a single circuit element both resistance and capacitance. So what we're going to do next is use transmission line theory to figure out the delay that using N-well resistors causes in your circuits, right? Because anytime, effectively, this is forming a laddered RC network anytime we use an N-well resistor. And so we need to figure out how much that's going to cause signal propagation delays if we wanted to use this thing for a digital circuit. And then when we talk about a couple of other layers, we'll talk about how they can be used as resistors and how they avoid this. But those other layers are not common to effectively every CMOS process, and the N-well is. So if you're building a simple, not 5 metal layer, not 2 poly layers and all this kind of stuff, if you're building a simple analog device, this is all you've got. So it's reasonable to actually cover it instead of saying you can do better by doing X. So anyway. Yes.
How is lambda determined? Is it just like the specifications of the material that works best?
So it's not the specification of the material because the material is practically always silicon. It's the specification of the foundry equipment that's being used to pattern all of this kind of stuff, right? So for a standard CMOS process, so this is at this point effectively up to around 24 nanometers. The cost to scale up and so to make things larger and smaller doesn't really change all that much because the procedure is effectively the same. It's just the tooling that gets changed at the particular foundry, right? So for instance, if you're like, when you design a mask, have you guys had to design masks for Chester or anything like that? What are the physical sizes for the masks? Yeah, a couple of inches by a couple of inches, and the features that you're patterning on there are probably a couple of microns by a couple of microns. You can actually use those masks to make features on a wafer that are much smaller than a couple of microns by a couple of microns by using like oils and stuff like that that have a different index of refraction so that effectively the pattern that's projected onto the wafer surface itself is smaller than the physical patterns that you've laid out, right? So going from one size to another is usually some sort of technique like that where it doesn't require a large change in the equipment or anything like that. But to go below that 24 nanometer threshold is enormously expensive because you can't just do simple things. So to get back to your original question, for a particular process, lambda is defined by the ability to reliably make something at that size,
Okay.
right? So it's all about the manufacturer. It's defined by the manufacturing process itself. It has next to nothing to do with the material, the semiconductor material you're making your device out of. It's all about, can we pattern it smaller or not, and reliably.
Okay.
Any other questions? So VD here is the reverse bias voltage. So VD is the potential difference across this guy effectively. Because we should observe that as VD becomes more and more negative, that denominator gets larger and larger, which causes the overall capacitance to decrease, which is what we would expect when we move those plates apart.